Well, thank you very much for the introduction. As you said, I'll be talking about Bayesian profile regression for multimorbidity clustering at population scale. So hopefully by the end of the talk, you'll know what that is, and hopefully, well, you might be able to see some useful applications of it in your own work. So before I start, I'd like to acknowledge the contribution of the co-authors that you see pictured here, the lovely smiley faces pictured here. So this work is based on a paper that's currently available in preprint form on the archive at that link. So the co-authors are Keith Abrams, Munir Pir Mohammed, Mark Davis, and Rhiannon Owen. Thank you very much to them from me. I'd also like to say thank you to HDR UK. This work was funded as part of the HDR UK Medicines Driver Programme. So I didn't actually get on to applying it to a medicines dataset, but I will mention how that work is continuing in the medicines context. So as I say, I'm going to talk about the paper that's on the archive, and the aims of that paper were to find clusters of multiple long-term conditions in electronic health records that were held in the SAIL databank. SAIL is the Secure Anonymized Information Linkage Databank. It holds healthcare and admin records for individuals receiving care in Wales. It's a very rich and diverse data set. There's lots of good data in there if you're not familiar. So the idea was that we wanted to find clusters of multiple long-term conditions, but also that had to have those clusters conditioned on like commonly adjusted covariates, so things like age, sex, deprivation, and so on, and also conditioned on an outcome. So in this particular case, we were looking at mortality as an outcome. So that aim, what we did to meet that aim was to write down a Bayesian profile regression model. So Bayesian profile regression is exactly that. It's a clustering model conditioned on covariates as an outcome. And as I say, I'll explain that, how it works through the remainder of the talk. In a population scale, so it's a Bayesian model. So Bayesian models are, I think it's fair to say that Bayesian models are more difficult, more challenging to fit than frequentist models. So we couldn't use MCMC, Markov chain Monte Carlo sampling. We ended up using SVI, stochastic variational inference, and I will explain that again as well as we go through the talk. So this work was done by kind of manually writing down the model using in a probabilistic programming language, a PPL. So it's good practice in that scenario to do simulation studies to make sure the model is doing what we think it's doing. So that was the third aim of the project. And okay, as I say, there's broadly three sections to the talk. I'll describe the model and how it works. I'll describe the fitting method SVI, and then I'll present some results. So Bayesian profile regression is a composite modeling framework. It consists of two model sectors. There are kind of two ways to think about how those model sectors interact, and I will talk briefly about. I see a hand raised. Would you like to ask a question now, or should we keep questions to the end? Okay.
Okay, yeah, so if we can, we'll keep questions to the end. We've got some time at the end for Q&A, if that's okay, Jim.
Yeah, no, that's fine. Thank you very much. So BPR is a composite model. So one way of thinking about it is in the context of multi-level modeling. So you see on the right of the screen here an example that's very commonly used to provide the case for multi-level modeling. So on the x-axis, you have socioeconomic status. On the y-axis, you have a test score, like an educational attainment score. And the example is showing that if you were just to use all of the data in one go, you would overestimate the size of the effect. But if you group the data into schools, which is represented by the color on this plot, you get a true estimate of the overall effect of SES on test score. So obviously in that scenario, you have to have all of the data that you need to fit the model. You need socioeconomic status, you need the test score, and you also need the school label. But if you imagine that for some reason you didn't have the school label, you didn't know which school children attended, an alternative would be to use Bayesian profile regression. So this is a slightly contrived example, but if you imagine that you had data on where the children lived, but you didn't know where they went to school, you could do some sort of clustering analysis, which you see on the left. So we have latitude and longitude of where the children live, and we've done some clustering analysis, and we have determined that it is most likely that children go to the schools that are kind of highlighted in red. This kind of analysis is kind of quite commonly done, actually, fitting a clustering model and then using results from that model to fit a regression model in like a two-stage approach. The difference here is that in a Bayesian profile regression model, the fitting is all done in one go. So the parameters in the response model, the multi-level regression bit of the model, are conditioned on the variables that are fit in the clustering model. That's quite an important feature of BPR. I will make some comments about why that seems to make a difference in the results for the multiple long-term conditions clustering when we get there. So a brief aside to talk about the clustering model. So the clustering model that is used in BPR is called the Dirichlet process mixture model. You may have come across it. I'm just going to briefly describe what a Dirichlet process mixture model is. So in this plot, you can see an example of a one-dimensional Gaussian DPMM. So the data here is actually what I would say before I get into the actual data is that the reference for this this plot, this guy's blog, Austin Rochford, is a very, very good example of a lot of different examples of DPMM. So if you're interested in Dirichlet process mixture models, it's well worth a visit to that website. This particular data set is times between the eruptions of a geyser in the Yellowstone National Park. So the blue bars represent the data, and when you fit like a distribution to that data, you end up with a solid black line, and that's the total density. The Dirichlet process mixture model will split that overall density into its component parts, and the Gaussian bit of the DPMM here is the fact that the components are Gaussian distributions. So you can see those are the dashed lines, and in this particular example, you see two Gaussian distributions are really really contributing the vast majority of the probability to the solid black line. Dirichlet process mixture models are very nice because they naturally work in a Bayesian framework, which means we can combine them very nicely with the response model. Another advantage is that you don't have to specify the number of clusters beforehand. It will fit however many clusters are useful to fit in the data. And again, that's another very nice feature. So we are using a Dirichlet process mixture model as the mixture sector of the Bayesian profile regression model. So what we're actually doing is slightly different to that example. Both of the previous examples, actually, the education and the geyser data. We want to fit, what we want to end up with here is a clustering on disease probabilities. So the data that's going into the mixture model is not continuous. It's not some continuous time measure or something like that. Each individual has a binary flag that indicates whether or not they have a disease or not. So that's the realm of a discrete DPMM rather than a Gaussian one. So on the left-hand side of this plot here, you can see, as I say, what we'll end up with is some measure of probability of, say, cancer and cardiovascular disease in this case. In reality, we're going to have many more than 2 diseases, so actually many more than 3 diseases, as you can see on the right of the plot. So in the results that I'm going to show you a little bit later, we used the Elix-Hauser comorbidity index for the disease definitions, which has 26 diseases in it. So that's the size of the latent space in the DPMM. Work is continuing, as I say, with the medicines application, and one of my colleagues, Tim Osborne, is currently continuing that work, and he's looking at scenarios where you have people taking potentially hundreds of different medicines. That sounded a little bit strange. Individuals are not taking hundreds of medicines. There are potentially hundreds of different medicines for individuals to take. So he is working on generalizing and fitting these models in those scenarios, which is a little bit more challenging than this scenario. So BPR is actually not a new modeling framework. It was as far as I'm aware, the first reference to describe it. Sorry, I'm not going to that meeting. I'm busy at the moment. Go away. Sorry about that. Yeah, the initial work was done by John Molitor et al. In this paper from 2010. That's the first reference I'm aware of for BPR. That's actually a very nice paper, and they describe a very similar scenario to what I'm going to describe to you, where the mixture model is discrete, and also the response is also a discrete outcome as well. So it's like a multi-level logistic regression model in the response. Since that paper, there's been continuing work over the years, and there's a very nice package that's been released, described in this paper by Silvia Liverani et al. Premium is the name of the package in R, and that's very accessible. It's very nice for doing Bayesian profile regression in R. They have written a custom sampler to sample BPR models using MCMC, and it supports several different mixture models and also several different response models as well. So it's very flexible and very useful for kind of having a go with this modeling framework if you want to do that. The difficulty with Premium for my application was that the data set was simply too large, and it would not work. It was unfeasible to get the sampler to fit in a reasonable amount of time. So that's what I wanted to say about BPR. Hopefully that's kind of given you a flavour of what BPR is. So I'm going to move on to the second section of my talk now to talk about SVI, stochastic variational inference. So it's very common in a Bayesian framework to use Markov chain Monte Carlo MCMC sampling. So the point here is that in a Bayesian framework, we want to calculate the full posterior rather than just the point estimate. We don't want to just, we want to retain full parameter uncertainty in the estimation. So that's, as I say, done using MCMC. Gibbs sampling, the no U-turn sampler, NUTS samplers typically are the most popular choices here. The difficulty with MCMC samplers is that they're very computationally expensive. So if your model is a bit complicated, like this one is, or you have a particularly large data set, which also the application that I'm going to present to you is, then fitting an MCMC sampler in that scenario is going to be really intractable. It just takes an unreasonable amount of time, and it's not likely to converge in, well, before you need the results. So what we need is an alternative to MCMC. Enter SVI. So SVI is a technique that reframes simulation-based sampling into an optimization problem. So if you imagine this blank slide represents the space of all possible posterior distributions that you could write down or you could derive from your model. So, I mean, if you can see my mouse, this point here would represent a different posterior to this point over here, for example. What SVI does is assume that your posterior is drawn from a subset of this space. So the circle that you see Q here is the set of posterior distributions that we are going to consider for our optimization problem. That's usually called the variational distribution or the set of variational distributions. So the way the optimization process works is you pick an initial set of parameters. That might be at random, that might be based on the data in some way, and that is labeled Q init on this plot. And then we compute a loss. So a common choice for the loss function that we would use is the negative of the expected lower bound of the Kullback-Leibler divergence, which is a bit of a mouthful. But yeah, the Kullback-Leibler divergence is a measure of difference between two statistical distributions, and the expected lower bound on that is a measure that's been derived that only requires one of those distributions to be known. So, as I say, it's a common and useful choice to use this expected lower bound. It's usually called the elbow, which is a nice acronym. So each time we take a gradient descent step, we move along through this space of distributions along this line, and hopefully we eventually end up at this yellow point Q opt, which is the variational distribution that's as close as possible to the true posterior, which is labeled P in green on this plot. So you'll note that in general, it's likely that the distribution that we find using SVI is not the true posterior. Actually, it's an approximation to the true posterior, but it's not the true posterior. And I'll explain kind of what that means for our results when we get there. So, and just a brief slide about advantages and disadvantages of the two different approaches. And I've taken the NUT sampler, the no U-turn sampler, as an example of an MCMC sampler here. So MCMC has these sorts of samplers have been worked on for many years, and they have lots of kind of mathematical machinery behind them. So I should say that NUTS is an approximation, but it's also true that as you take more and more samples, as the number of samples that you draw from NUTS goes to infinity, you approach the true posterior distribution, which is a very nice advantage to have for NUTS. As I said on the previous slide, there's absolutely no convergence guarantees in SVI, and in general, actually, the variational distribution that you find is not the true posterior. As I say, people have been working on these samplers for many years, so there's lots of kind of convergence diagnostics available to check to see if your fit has converged for NUTS and for MCMC in general. So things like R-hat, which measures chain mixing, autocorrelation, which measures it's a measure of convergence. So SVI does have some convergence diagnostics, so you can, but they're a little bit more limited. So you're pretty much limited to looking at the loss and seeing to make sure that doesn't change over sequential iterations to see if your algorithm has converged. I mean, obviously the big advantage here for SVI is computational efficiency. It is a heck of a lot faster than the NUTS, and in fact, it is feasible to fit complicated models to large-scale data with SVI, where it just simply wouldn't be with NUTS. So what I'm going to present now is some results. Firstly, I'm going to talk about results from a simulation study that we ran. So these plots are a little bit busy, so hopefully they're clear. So they'll become clear anyway as I describe them a bit. So on these are both plots of the coverage of some parameters. So on the left, you have the coverage of what's labeled the phi value. So phi is a probability parameter in the mixture sector of the model. So what you can see here is the stars. Hopefully you can see those, but stars represent coverage from a nuts fit, and dots and crosses represent coverage from SVI fits. And you can see on that plot that they're all kind of broadly in the same sort of ballpark. So the SVI coverages are a little bit lower than the nuts coverage. I should also say that coverage is a measure of how well the uncertainties are captured in the model. So if you it's the statement, a 95%, a coverage of 95% indicates that 95% of the time, the true parameter falls within the 95% credible interval. Hopefully that was clear. So, as I say, the parameters in the mixture sector of the model, they do kind of match up quite nicely, I think, with the two methods match up quite nicely. They're not too dissimilar, which indicates that the SVI distribution for that sector of the model is actually not a bad approximation to the true posterior. So on the right, you can see the same plot, but for the gradient values in the response model, and you can see here that the coverage values are quite a bit smaller for the SVI fits compared to the nuts fits. So that's indicating that the posterior distribution for the response model is not such a good approximation. So these are the results from the analysis of the data held in SAIL. So I should say that this is a general population. So there's no inclusion criteria requiring people to have a specific disease or a specific age cutoff or anything like that. So the population is nearly 1.3 million. Mean age is 42.5 years old. The heat map that you see on the right shows the disease probabilities fitted in the mixture sector of the model. There's quite a lot of information in here. So the model found 33 separate clusters, and as I said previously, the diseases are defined according to the Elixhauser comorbidity index. So along the top row, you can see that that's the outcome probability for each cluster. So the outcome probability was mortality, and the top row is how likely females were to die, and the next row down is how likely males were to die. So the yellow color on this plot indicates a high probability close to 1, and blue indicates a probability close to 0. So if I just pick out some results from that plot, again, this is maybe quite a busy plot, and I'm sure it's not tremendously helpful for people with color blindness. I apologize for that. I was running out of colors when I was making this plot. So what I've done here is try to highlight the clusters that feature cancer prominently. So the orange color on the left indicates the one cluster that has a relatively high probability of cancer, but not a high probability of metastatic cancer. So just pre-metastatic cancer. The clusters that are highlighted in red and pink are indicating high probability of both cancer and metastatic cancer, and there are 7 of those clusters. So again, cancer is quite a complicated disease. It's not just one disease. I was very fortunate that one of my collaborators on the paper was and is an oncologist, so he was very knowledgeable in this area. Mark Davis, thanks to him. So I will just flag up the 2 clusters that are highlighted in pink, which, as I say, hopefully you can see. So there's cluster 8 here, labeled in pink, and cluster 14 down here. So both of those clusters have, as I say, a high probability of cancer and metastatic cancer. but they don't really have a tremendously high probability of other diseases. It's really just cancer in those clusters. But the outcome probabilities are very different. So cluster 8, the cluster on the right, it features a very, very high probability of cancer, of mortality as the outcome. And it's likely that that cluster represents people who are either diagnosed very late, they have very late stage disease, or the cancers that they have don't really have much in the way of treatment options. So things like pancreatic cancer is a common example there. The other cluster 14, that has a much lower outcome probability, that one potentially represents less aggressive metastatic cancers that have more treatment options available. So potentially things like prostate cancer these days, which is often treated as a chronic disease rather than an acute one. So this, I think, is highlighting one of the real advantages of Bayesian profile regression and fitting a single model in one go that features clustering and response. If we were to look at a clustering followed by a regression model, for example, then this wouldn't have been picked out. The two different clusters featuring just cancer and the different kind of outcome probabilities would have been just collected as one. Well, it's very likely it would have just been collected as one cluster in that sort of analysis. So I think, well, I hope I've given you a flavour of what Bayesian profile regression is, and I hope I've been able to persuade you that it allows for granular clustering conditioned on covariates and outcomes, and it's potentially more useful than a two-stage modelling approach. I also hope I've given you a bit of a flavour of SVI and how it provides reasonable parameter estimates, even though the uncertainty quantification is not as good as you'd get with an MCMC fit. So some future work that I think would be useful is if we were to include different regression model responses. So there's lots and lots of options there that we could use in the GLM family. Also, things like time to event models are quite useful would be quite a useful feature to have. I should also say that all of those responses are supported by the premium package. We could also look at developing more exotic mixture sector structures. So the obvious ones to use there are where you have continuous data. You could use a Gaussian mixture model. There's lots and lots of other options there for different data types to include in your mixture sector. So thank you very much indeed for listening. That's all I've got to say. There's a link there that will take you to a GitHub page that has my slides and some notes on there. But yeah, happy to take any questions.